Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. This week is going to be the 12th and the last week of this course. And I really hope that you have been enjoying the course throughout. Of course, the course consisted of many new and very interesting topics of astrophysics and space physics. But it also consisted some non-trivial mathematical techniques. Sometimes I followed step by step some derivations, and sometimes I just deliberately skipped those. Okay, but the main objective of this course was to give you an exposure to the ongoing research, okay, on this domain. Okay, that means the astrophysics and the corresponding fluids. Astrophysics consists, starting from the solar physics, planetary physics, stellar physics, etc. Okay, we did not really cover planetology part, okay, but at least the solar physics and the other stellar bodies we tried to cover as much as possible, although most of the time in a superficial manner. In this lecture, we will continue our discussion on turbulence in fluids. Okay, still we will just talk about normal hydrodynamic fluid turbulence, okay, and also for the incompressible fluids. So in the previous lecture, we already introduced the definition of turbulence, okay, the practically how to characterize the turbulent flow, the corresponding important concepts like the energy cascade, the universality, Kolmogorov's -5/3 law, exact relations, this type of thing. So today we will mostly discuss some a very practically important topic, that is the turbulent diffusion. Okay, and why this topic is important both for everyday life and for astrophysics we will discuss when I will elaborate several aspects of this topic. So, if you really followed the previous discussion on turbulence, you will easily understand that till now our basic assumption was that the turbulent flow is considered to be in a field which is statistically homogeneous and also isotropic. Okay, but here just we are, I have just taken for convenience just this assumption of statistical homogeneity. Okay, now let's say we have a system where even the statistical homogeneity cannot be applied. That means the system has a very strong local, very strong gradients. Okay, for example, if let's say if you have a flow field in which this part and this part, they cannot be compared with each other. Okay, so in this case you can say that the turbulence over here cannot be just put with the turbulence on here like in a global homogeneous framework, right? So let's say then you have to take the subdomains like this and this, and within each subdomain you can like think of homogeneous turbulence. Okay, now let's say instead of just this type of two regions, you have several regions. Okay, and then actually for every subdomain you can still apply the assumption of statistical homogeneity, but the only thing is that if you globally consider the system, you should understand one thing, that this type of system should permit transport phenomena. Okay, because there is a gradient. So for example, one simple gradient is the gradient of density. Okay, let's say your system is such that here the concentration of some fluid is very high, and here the concentration of the fluid is a bit lower, here a bit lower, and here this is very low, and here this is almost nothing. Okay, that is because maybe maybe in this point you have a source of the fluid. Okay, so and every time, so it is true that then you can say that after some certain time there can have some homogeneity, but let's say you have a sink at this position, then although from the source the fluid is coming, okay, then this fluid will again try to vanish by this sink at that point. And that's why, to be very honest, in your system there will be always a steady gradient, okay, gradient of the density of the fluid. Now in this type of situation, what you can really expect from your previous knowledge of transport phenomena, you can expect some phenomena like diffusion, okay, and this will be then very interesting to study the diffusion in a turbulent flow. So I mean, we are now assuming that the flow is turbulent because the Reynolds number is very, very high. So the flow, I mean, the non-linearity in the flow field is totally dominating. And in addition, we have a transport phenomena like diffusion. So in this case, we have to consider two things side by side, diffusion and turbulence. Okay. So basically we are interested to the study of the effect of turbulence on diffusion, okay, or you can say to study the diffusion in a turbulent flow, okay. Now it is true that since in a turbulent fluid the fluid elements carrying different physical properties, okay, physical quantities, for example velocity, density, pressure, whatever, move randomly, then it is somehow expected that turbulence enhances transport process, okay. Now of course this is true that turbulence I mean will help, I mean that is something very, very much intuitive, that it will help in mixing, right? So just take the very famous example of adding some sugar or milk in a cup of coffee or tea, okay. Let's say you just add drop by drop milk and you don't stir, or you add some sugar, okay, in the cup of coffee or tea and you don't stir. Of course they will mix, but they will mix in by normal diffusion process, and that is a very slow process. What you in general do, what we in general do, we stir the system by a spoon or a stirrer, right? Then it gets mixed, okay. So this is something very, very intuitive, that turbulence can actually make an efficient mixing. That is only because that in the I mean, for a good mixing, what you have to have, you have to have a very randomized motion of the fluid blobs or fluid packets, and turbulence exactly does that, okay, because of the non-linearity, okay. Now this formulation, well, it is easy to say in words what turbulence does for efficient mixing, but for the first time the first formal formulation was given by Taylor in the year of 1920, okay. This is the same Taylor who talked about the importance of 2-point correlations in turbulence, okay. So in a sense, Taylor can be thought to be the father of, so-called modern turbulence or modern fluid mechanics. Okay. Now, as I just said, that in everyday life, we need this turbulent diffusion for the mixing of milk and sugar in tea or coffee. And what happens that without stirring, the process is very slow. So mixing by molecular diffusion may take hours or days. But would you wait for that? Of course, no. You need some fast process so that you can have your tea or coffee sweet or totally mixed with milk in some seconds. Then you just start the system, and then it is mixing by turbulent diffusion. So we understand phenomenologically that what is turbulent diffusion. That is something where the diffusion or the mixing, or the transport due to the gradient of density is done in the presence of turbulence. Okay, but the question is that how to do some quantitative thing out of that. Okay, so in order to do that, let us start by doing some how to say, some tracing. So first we use some tracers to follow some fluid particle. That means in a like container of fluid, you just use some fluorescent elements. Okay, so you just drop some fluorescent color type of color points, and then you just like follow the trajectory of those fluorescent points. Because here I have drawn a lot of fluorescent points. What you will do, you will just put something like this, and then you just follow this trajectory. You will see one trajectory will go there, one trajectory will go there, one will be going there, one will be going there, one will be going there. So it's a totally abrupt process. I mean, it's a totally random process. Okay, disordered process. Now if we do that, then the displacement of a tracer marked particle is given by, after some, so if you just start your watch at t is equal to, let's say, 0, and then you stop your watch at small t is equal to capital T, then you will say that my displacement vector at small t is equal to capital T is given by x, which is a function of capital T, will be simply equal to integration 0 to t Lagrangian velocity of the fluid particle integrated over dt. That is because simply dx dt is nothing but VL. Then you just integrate to get x. Okay, as simple as that. So exactly just like we are trying to track Newtonian particles. Here we are just doing the same thing for Lagrangian particles or fluid particles. Okay. Since we consider a totally random or disordered motion, one can intuitively easily assume, and which is a quite reasonable assumption, that the mean displacement of all these displacement vectors will be equal to 0. Of course, there will be a vector sign here. Okay. Frequently, I can see people do not make this vector sign, but this is a null vector. Okay. So the average of the displacement vector is 0. That's simply saying that if you take a number of such fluid particles, and you just, as I just said, that in a container you start by saying, okay, I have a number of fluid particles very localized, and then if you just track, you will see that this one can go there, this one will 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 go there. Oh my god, this is a total mess. And finally, if you just calculate them, the vector sum of all these things with respect to some specified origin, it will be 0. Okay, or it will be very, very close to 0. But of course, the mean square displacement vector is non-zero. I mean, mean square displacement, it's not a vector, I mean in general, because this is taken as a square, so the mean square displacement is not non-zero. And this is given by this angular bracket x square, which is also a function of capital T, and that will be simply equal to double integration. One integration will be on t, small t, another integration will be some another time, okay, time coordinate tau, and this double integration will be done on the 2-point velocity correlation functions of the Lagrangian velocities, okay, of two different time points, one at t, small t, one at tau. Okay, so if you do that simply, so what we can get, if you integrate the Lagrangian velocity at a given time point, okay, over time you will get the displacement vector at that time point. Now if you take the 2-point velocity correlation function of the Lagrangian velocities, of course, okay, and then you integrate them in time, double integration, then what we will get? We will simply get the mean square displacement. Okay. Now, once again, you have to easily understand those things, that these are the velocity of some fluid particle at different point of time, not different point of space but different point of time. Okay, and due to this different point of time, actually they will be at different point in space. Okay, so that means here the space position is explicitly changing with time. Okay, is this part clear? So this is like you are just tracking a particle. So the particle has a VL, okay, at let's say some time instant small t, but at small t that particle is at let's say small xt, okay, and at some time tau the particle, let's say, at position x tau. Okay, so you will see that when we are talking about the two different time points, it is actually synonymous of saying that they are of two different positions. Okay, but here simply the position is explicitly depending on time. Okay, that's why we just write the functional dependence of the VLs directly on time. Okay, now note that just like statistical homogeneity, if we assume here a new assumption, which is the assumption of statistical stationarity, then what happens? So statistical stationarity is nothing but a homogeneity in time. Then what happens? Then the 2-point correlation function will simply be given by the normalization constant, which is VL square averaged times the Pearsonian correlation coefficient, and this correlation coefficient will then simply be a function of neither t nor tau but the distance between t and tau. So it will be a function of t minus tau. So one can simply check where when t is equal to tau, then r0, this will be r0, and this will be v tau square or vt square, and this will also be v tau square or vt square averaged, and these two average will cancel each other to make r0 to be equal to 1. Okay, now one thing here I would like to say that so here we are just talking about stationarity because this is something very important for our case. And remember, in the previous discussion I mentioned that Kolmogorov, when in the year 1941 he obtained his famous exact relation, which was relating the the third order structure functions or the third order moments of the 2-point increments along with the length scales, then specifically he considered stationary turbulence. Okay, so statistical stationarity is simply means that any statistical average, okay, any statistical average is explicitly independent of, there is no explicit dependence on time, so that will be 0. And also this type of time, this type of correlation functions, 2-point correlation functions in time will simply be a function of the difference between the two time points. Here we have to understand that just by definition, that is just one point to remember, just by definition, this VL which we say, they are not really the normal, the total Lagrangian velocity. They are the fluctuating Lagrangian velocity with respect to the mean value or some background value. Now here it is equal to the total velocity, okay, only when we are starting, only when we just make the mean value, so the mean value of this thing to be 0. Okay, and that's exactly what we are doing here. Okay, so VL should be such that the VL mean is also 0. Okay, So and that is not a very difficult thing to understand from here, because this is 0. It can actually say that ddt of x, this is also 0 in some way. Okay, I mean, just think. Okay, so VL is also randomly distributed, so average of VL is also 0, and that's why just by writing the total velocities are equivalent to writing their fluctuation with respect to their mean, because the mean is 0. Okay. Now here one point to note, not really directly related to what I have just talked with that, but one point that here very often we also use another symmetry which is called the mirror symmetry in time, and that is very easy to understand, because in time, okay, homogeneity simply means that this is there will be, I mean, the property, some physical property will be invariant in by time translation. So the time translation in positive direction or negative direction should be made equivalent if we are talking about 2-point quantities, right? And that's why if this is r of minus tau, that means some, so let's say VL t plus tau times VL t, if this is a function of tau only, then of course VL t minus tau times VL t, okay, will be a function of some function of minus tau, and there is no reason to say that these will be in any case different from, because this is totally statistically finally averaged, there is no reason that that will be different from this thing. Because in both cases you are just taking the averages of all the couples who are tau distance apart. And here actually in time you don't have a vectorial property. So I mean, you are on one axis, only one axis is there for time. So this is trivially, I mean, understood. Now for stationary turbulence, we can write this thing. So if we now consider stationary turbulence, the mean square displacement, our final objective is to determine mean square displacement. Why I am coming later. So the mean square displacement x square t, which is averaged, is equal to integration 0 to t dt angular bracket VL square. VL square is something which is constant, so it can go anywhere. Again integration 0 to t d tau r of tau minus t. Now this thing, when this will be integrated over tau, it will simply be a function of small t only, and then this will be integrated over dt. Okay, this part we have just obtained by using this relation and then this expression of the 2-point correlation functions. Okay, this one for stationary turbulence. So this is general definition. This is true for stationary turbulence, and this is also true for stationary turbulence. Okay, now we have to understand what we are looking for. Okay, so if we are looking for, just to check that the system's behavior very near to the origin of the time, that means you just start your clock and you just stop it. Okay, so you are just checking the system's comportment or behavior by how to say, during a very small time, and that time is very small with respect to the correlation time. Now correlation time is nothing but the time beyond which the 2-point velocity correlations are decreased by by a significant amount. That means by 67%, rather, almost. That means 1 by e. Okay, part. So if it starts from, if the initial value is like 1, let's say at time t is equal to 0, if r0 is 1, then I mean after, so it should look like this correlation functions, and after this time t core, okay, so this rt core will simply be r0 by e. Okay, so this is the simple thing. Now if you want to be in such a time which is very small with respect to the correlation time, so correlation time, let's say over here, and here this let's say you want to be here, so that means that your correlation is almost 1 here, so no further, no much deep, I mean no much decrease in the correlation coefficient. So then this can be assumed to be 1, and then what else? This is constant. This will give you capital T, this will give you capital T. So you will simply have your mean square displacement will be equal to some constant time t square. So when we are in very short time, the mean square displacement is proportional to t square. But when, so it will have some parabolic relationship with t. Now let's say we want to check the statistical properties of turbulence. Then what we have to do, we have to investigate the system's behavior in time which is very greater than the correlation time. Then only we will check the statistical properties of the turbulence. Okay, so because if your time is long enough, then only the 2 points will be very weakly correlated, and you can simply see the effect of the turbulence in the system. Okay, so how to say that? That means that so let's say if you like put your reference time which is very large with respect to the correlation time, then what happens that inside that time interval you will simply have so many correlation times, so many correlation times, and that will give you a statistically very well trusted sampling. Okay, so and if your time is within the correlation time, so it simply means that your system is not statistically very trustworthy. Okay, so if you want a bit more knowledge about that, the correlation time and this type of thing, so you have to check. So any introductory textbooks on statistics or time series analysis type of thing. Okay, so that is one thing. Now if we are in this just a minute. Now if we are in this position, then we can say that this mean square displacement will simply be VL square averaged, which is constant, so comes out integration 0 to t dt integration 0 to t d tau r tau minus t. Now since we are interested in the time which is very greater than the correlation time, what happens, we can simply say that we can easily replace this integration just by saying that this is almost equal to the everything unchanged, this integration with a changed boundary minus infinity to plus infinity. So instead of 0 I just write minus infinity, because before 0 the correlation doesn't have any contribution, and if my time is very large, then I can say that if instead of t I write now infinity, there is no change, because let's say if my correlation function is like that, sorry, not a very good drawing, like that, and then I say that okay, my t is here, for example, then just by saying t here or here doesn't make any difference, because the extra contribution which is made, which is perceived just due to this choice of t and is really negligibly small. On the other hand, if my t is over here, then I cannot say that my t can be assumed to be at infinity. But when the t is very near to the end of the tail, then you can say my t is almost equal to infinity. So if I just put there, then just defining a coefficient called dt, okay, which is equal to 1 by 3 angular bracketed VL square integration 0 to infinity r tau d tau, we can simply write the whole expression to be equal to 6 times dt times t. Here there is a small cheating, mathematical cheating. What I did, I just said that after this integration there should be some, to be very honest, this thing should have some t dependence, but this t dependence we have just neglected over here, and so that this integration is done independently of this part. So practically these two integrations have become uncoupled here. Okay, and I am just saying that this integration does not have a very strong t dependence. Once this is integrated over tau, this is already done. That is only because I am saying, because that when I am talking about very large t or very large tau, then what is happening at tau very large does not really matter, okay, from the from the t, and that's why that the dynamics of this part can, to be very honest, to be thought of decoupled from this part. Okay, once this is simply integrated over this, you can get almost a constant coefficient. So I am just saying that I am here neglecting the explicit time dependence of this coefficient, and if I neglect that time coefficient, time dependence of that coefficient, then this time mean square displacement simply becomes to be proportional to the t, to tau, or sorry, capital T, to time. So if we are at time which is sufficiently greater than the correlation time, then the mean square displacement simply follows a linear relationship with time. Okay, and that's exactly something which is very interesting, because this has a striking similarity with diffusion. Okay, you see that here in the whole process we have not talked anything of diffusion. We simply started by 2-point correlation and stationary turbulence, and we have arrived to some relation of the mean square displacement where we see some similarity with the diffusion. Why? Because if you just now use your previous knowledge of diffusion, you can see that the diffusion equation for the density should be given by this: del n del t is equal to d Laplacian n. Okay, and so n is the density, and this is something which is the variable in the diffusion process. Now let us just consider a spherically symmetric flow in this case, and then the mean square displacement term should simply be given by integration 0 to infinity r square n 4 pi r square dr by just integration 0 to infinity n times 4 pi r square dr. This is the whole this is the whole number, okay, of the particles. So this is just used to normalize this number, okay, and this is, here you see that the r square, this simply gives me finally the mean square displacement. Okay, so this is an second order moment in some sense for the displacements. If you do that, then you have this expression and again just using this equation and integrating them again in space for a spherical symmetric system, you can again obtain this type of thing. Okay, this simply comes from the diffusion equation. If you integrate both sides just in space using spherical symmetry, nothing other than that. This is nothing but the spherical symmetric form of the Laplacian. Okay, and now if you carefully calculate the right hand side by integrating integration by parts, this part, you will see that this part, the part is equal to this 6 times d times integration 0 to infinity n 4 pi r square dr. Now there is a del t, so finally again integrate, you have to integrate over time, and finally you will have some this term over here, and then del t goes in this side, and then by integration it will simply have 6 dt. Again this thing I have assumed that to be independent of time. Okay, that is my assumption. If I assume that, and we also assume that this is also fairly uniform over time, this this thing, and then this integration over time is simply the integration over dt, and you have again something like this, and then you have that by definition your mean square displacement is nothing but this one by this one, right? If you remember the definition which is given here, and then finally you will have this one is equal to 6 times dt. So you see, so that is the classical formula for mean square displacement in a diffusion process. And so as our d capital T is similar to this d, then we can say that what we find over here is nothing but a diffusion process, and this process is known as turbulent diffusion. Okay, and that is exactly the process which leads to a quick mixing of sugar or milk in a cup of tea or coffee. Okay, thank you very much.